solder this into a circuit, it usually changes its resistance permanently. Okay, not by a large amount. Okay, by a couple of percent. All right. Also, if I load cycle, if I apply a high voltage to it and then turn it off, high voltage to it and turn it off, and that's the kind of thing that might happen. That also will probably permanently change it. Vibrations, high vibrations can change the resistance, humidity, all sorts of different things. Okay, that's something to kind of keep in mind. Now, there's the types of materials. This is what's called a carbon composition resistor. Different materials have different behaviors. Usually when you need precision, you get one of these types right here. This is a 1% resistor. Okay, the blue ones are usually 1%. And it's metal film. This one's carbon film, okay, or carbon composition. This one here is metal film. Metal films are usually quite a bit better in terms of how they behave. Okay, 1%, and then they're more robust against variations in applied voltage and temperature and humidity and things of that nature. When you need power, you go to something like this. And this is high tolerance resistor, but you can get a low tolerance, a really precise power resistor if needed. Okay, and oftentimes you do. Power resistors, a lot of times you need to use them to measure currents and things like that, and they need to be very, very precise. All right, resistors are pretty boring though, and so we're not going to say too much more about those. Capacitors and inductors are really where things become a little bit more sort of intriguing to some extent. Okay, now capacitors, same thing. They are, and this is where it really gets into stuff that's going to affect you in the lab. Okay, so if you've been zoned out, you're probably going to start zoned back in. All right, so with a capacitor, again, they vary with temperature. They have a tolerance. They have all that sort of stuff. But they also have power limits, and they also have voltage limits. So there's a maximum voltage that can be applied to a capacitor. There's a maximum power that can flow through it. Okay, and that might be a little bit strange because capacitors supposedly don't dissipate power, but they do. All right, a real capacitor does, and that's something we got to talk about a little bit. All right, so let's get the basic picture. So when you're in Adams's class and he's talking about capacitors, all right, he's probably going to draw you a picture that looks something like this. You're going to have a plate, basically two plates. All right, and there's going to be positive charges here and negative charges down here. Okay, and in between that plate is going to be some sort of material called dielectric with some permittivity epsilon, and the capacitance should be what, epsilon A over whatever this length is here. We'll call that length D. All right, so it's epsilon A over D, okay, where D is the distance between the plates. All right, that's our basic formula for capacitance. Most capacitors don't quite look like that, okay? The basic ones that you guys see that do kind of look like that is the ceramic disc capacitor, okay? Where these two leads go in and they actually do attach to some kind of a disc. And then there's some sort of material between them. So I call that a ceramic capacitor. So guess what? The dielectric in between there is going to be ceramic. Okay, so let me go back here to sort of a cutaway picture of it. Okay, so this is what, if I were to do a cutaway of that capacitor, here's what it would sort of look like. All right, so you guys can see that. Basically, you got this outer coating in there. So it's something that's been dipped into. And the leads, so that term you may not be familiar with, but leads are the things that basically allow you to connect into this thing. The leads are connected to some sort of a metal plate. In this case, it's a silver electrode. All right, and what you have, if you look at that there, okay, you see that what you have is a plate here and a plate here, and then in between them, that red, number 5 there, is some sort of a ceramic dielectric. Okay, and they're not spelled properly, it should be EIE, okay? That's what happens when we get stuff off the internet. All right, but that's basically what's inside of that thing. So that's the basic picture. Now, all right, what's good about this? Well, this ceramic can usually have a pretty high voltage across it, or reasonably high voltage, maybe a couple hundred volts. All right. What's good about this thing is it has a good frequency response. We'll talk about what that means a little bit as we go. All right. But for now, suffice it to say that the frequency response is pretty good. Now, one real drawback to this thing is, well, let's go back to this basic expression. This epsilon can be made big, but not too big. Okay? All ceramics have a particular epsilon. The thing is, if I really want to get a big capacitor, I can't get things too close in there. The key thing is usually that I have to make the area really big. So if I want a big value capacitor, if I want a farad, okay, this thing would become enormous. So enormous that it's not at all feasible. All right, so if you want a big value capacitor, what you're probably more used to is having dealt with this guy. Okay, that's what I'm going to call an aluminum electrolytic. An electrolytic, but an aluminum electrolytic. All right, so it's some kind of a canister. All right, now you can start to see some of the limitations on this guy. All right, so you can see on there maybe that it's rated for 50 volts. Okay, in other words, I can only put 50 volts across this thing. If I start to put more than that across there, it's going to blow up. And as you guys know, also if I probably apply negative voltage on this, it's going to blow up. All right, the longer lead is usually the plus terminal. The shorter lead is the minus terminal. Okay, there's usually also a lighter colored stripe on the side with the minus terminal. Okay, so that's kind of key. Now, this guy's not that much bigger than this one. All right, this one here is, and now here's a good time to show you guys how to read capacitors. All right, so if I look on there, I'm not sure if you guys are seeing that too well. You're probably not. I'll tell you right now, it says on there 101. All right, in fact, it says 101J. And that J says something about the tolerance, okay, what the variation is in this. But that 101 tells me how to read the capacitance of it, okay? So let me write that out. 101, the way I think of this is like so. It's basically 1, 0. So I write the first two numbers out. And then this tells me how many zeros to follow that with. It's that many picofarad. Okay? So everything's written in that way. So 100 picofarads or 0.1 nanofarads. Okay? Now, similarly, if it had been, let's see, I think I got another one here. Okay, this one says, you can't see it, but this is one of the options you guys will have in the lab. This one says 824. Okay? What does that mean? That means 8